All right, 6.5. Okay, so 6.5, put it over here. Let's make it a little fatter. Lesson 6.5 is growth and decay. Growth and decay. And it's today, because it could be any day. All right. Growth and oh, that looks horrible. Decay. Yeah, well, that's like a fancy Y. Okay, so exponential growth, exponential decay. Many real world scenarios involve them. Exponential growth occurs when output quantities increase exponentially over time. Some examples of exponential growth include bank interest, population growth, and bacteria growth. Ew. Exponential decay is shown by output quantities decreasing exponentially over time. So decrease, down, which is, an example would be car depreciation. As soon as you buy a car, it starts depreciating, which means it goes down. Population decrease, radioactive decay, exponential functions can be written in a model. These situations the function can be used to predict future values. Okay. Solving growth and decay application problems. Number 1, determine the y-intercept, which is AKA, so let's write this down. Number 1, y-int, AKA starting value for the situation. Number 2, determine the constant multiplier for the situation. Constant multiplier. So is it growth or decay? And if dealing with percents, add or subtract the percentage rate from 100. So percents, you're going to do 100 plus or minus the rate, and then make it into decimal. And then 3, write the exponential function by filling the y-intercept b in constant multiplier m, like we learned in 6.3. So you're going to write it like this. F of x equals the initial, or the starting point, which is the y-intercept or starting point, times the multiplier to the x value. And then 4, answer the question by substituting information from the application problem into equation by solving. Solve. All right. Oh, a little too much. Okay. Let's go to the next section. All right, so in order to determine if you should add or subtract from 100 to find the constant multiplier, you must know, okay, so growth. We'll do that in orange. Growth goes up, obviously, so you add to 100%. Okay, and then decay, you would subtract from 100%. So other words for growth: increase, up, raise, appreciate, not like I appreciate you, but it goes up, earn. And then for decay, it would be decrease, down, drop, depreciate, lose. All right. All right, so pretzel 1. All right, so pretzel 1. The water in Will's swimming pool was 88% Fahrenheit at the beginning of the month. So at beginning, water in pool was 88% Fahrenheit. Okay. Each day, the temperature of water went down 2%. All right, so literally 2% per day. A, write an exponential function. Write an exponential function for this situation. I'm just going to write an exponential function for this situation. I'm not going to write it down, but you guys can hear me. Where x is the number of days from start, and okay, that's it. All right, let's do that first. All right, so at the beginning order, okay, perfect. So you would say the beginning was temperature in the pool started at 88 degrees. That's the start. So my start is 88 degrees. And it's going down by 2%. All right, so remember it's out of 100, so it's dk. So it's 100 minus 2, which gives you 98%. And then you're supposed to change it into a decimal or decimal. Wait. Oh my gosh, I totally forgot how to say it. You're going to change it. You're going to change it into a decimal. Did I say decimal before or a demisel? Anyways, you're going to move it over twice, and that would give you 0.98. So my equation would be f of x equals b, which is 88 times 0.98 to the x. Remember, if this number right here is less than 1, it's a decay. If it's more than 1, it's an increase, okay? So just remember that. All right, so there's your answer for A. Now let's go to B. All right, so B says, what will the temperature of the water be after 10 days? After 10 days, question mark. We'll make that one pink. All right, so 10 days. So you're literally going to take that and sub it into your exponent, which was at the beginning of the water pool, temperature of the water is right here. Oops, oh, right here, the x. All right, so I'm going to do 88 times 0.98 to the 10. And then I literally am going to put in my calculator. And it wasn't perfect, but I'm going to round to my nearest tenth. So it's approx 71.9 degrees Fahrenheit. So I'm going to say after 10 days, the temp in pool will be approximately or about 71.9 degrees Fahrenheit. There's your answer. Yay, pretzel 1. Okay, pretzel 2. And remember, you can always pause and rewind and listen to my beautiful, beautiful voice. Pretzel 2. Memorial Middle School, OPA, Middle School. Enrollment increased by 3% per year. There are currently 640 kids. It says students, but it's easier to write kids in the school right now. Approximately how many students will attend OPA in 5 years? Yay! Okay, so first my initial is 640, and it increases by 3%, which means you're going to add it to 100, which gives you 103. And remember, you change it into a decimal. So then your equation would look like f of x equals 640 times 1.03 to the x. All right, so you're going to put 5 into the x. And then you put that in your handy-dandy calculator, and you're going to get about 742. So you're going to say OPA, OPA will have approximately 742 students in 5 years. Yay. All right. So before we go to example or pretzel 3, we need to write some notes. So, exponential growth and decay. Exponential growth, exponential decay. So for exponential growth, you would have f of x equals the initial. Remember, it's growth. It could totally make sense, so you do that. But make sure you always change your percent into a decimal, okay? And then for exponential decay, it's the same thing. But since it's a decay, you're going to take away from 1, which is 100%. All right? For example, if it grows by 7%, it'd be 1.07. If it decays by 7%, you take it away, so it'd be 0.93. Because it's less. And remember, less than 1, it's a decay. Greater than 1, it's a growth. Okay? All right, let's go to, new piece of paper. Pretzel 3. Okay. So we'll use Finn. Finn's baseball card collection appreciates. To appreciate means to go up, you guys. Appreciates by 2.5% per year. If it is currently worth, so currently it is worth, good job, Finn, $135. How much will a collection be worth in 20 years? Okay, so f of x equals 135 times, and then appreciates means to go up, so I'm going to add to 100 and then move it over twice. So that'd be 102.5, which would be 1.025, and that's to the x. And then in the x, I'm going to put 20 years. And it's going to be approximately 221.21. So I'm going to put Finley's baseball card collection will be worth about $221.21 in 20 years. Yay, good job. All right, that was it for 6.3. I mean, sorry. That was it for 6.5. Let's go to 6.6. Okay. See you guys at 6.6. All right.